KnowGraph is a personal knowledge graph built from scratch. It captures technical concepts, organizes them by topic, and maps precise relationships to one another. Highlighting any concept triggers a large language model to execute an immediate, highly specific deep dive into the material, turning the static map into an interactive learning engine. Stripping away the interface reveals a full-stack monolith built without external abstractions. 3 layers communicate continuously: a React Frontend at the top, a Node.js API in the center, and a PostgreSQL database at the bottom. This entire architecture runs on one isolated Ubuntu virtual server. Refusing to outsource server management, deployment, or database hosting forces a complete audit of the data request lifecycle. Owning the bare metal infrastructure requires understanding exactly how bits travel from a database sector to a pixel on a screen. If we isolate the topmost tier, this diagram shows the React frontend. This is the only part of the application that executes entirely inside the user's local browser memory. During development, this environment relies on Vite, a build tool that facilitates sub-second hot reloading. When a source file is saved, Vite pushes the exact changed module directly into the browser. For production deployment, Vite compresses modular files into HTML, CSS, and JavaScript. The visual styling within those files is governed by Tailwind CSS. Rather than writing custom cascading style sheets, developers apply predefined utility class names directly onto the HTML structural tags to enforce a uniform design system. This diagram illustrates the D3.js implementation controlling the visualization logic. A continuous physics simulation calculates the layout on the fly. Vector arrows push nodes apart, while connecting edges pull them together. The visual mapping is literal. Abstract concepts act as physical nodes, relationships providing structural tension. Because this entire interface is trapped inside the user's browser, it requires a dedicated conduit to fetch data. A single wrapper script, labeled API.js, manages all outbound HTTP communication to the server. Every time the user clicks a visual node or saves a text note, this wrapper script intercepts the request. It extracts a cryptographic authentication token from local storage and rigidly attaches it to the network request before allowing it to leave the machine. A modern frontend is a bundle of static text files, relying on a unified network conduit to pull dynamic state from the server. Moving down to the middle-tier API, this schematic shows a Node.js runtime executing an express framework, sitting above 3 distinct logic paths. Node.js allows JavaScript to run natively on the server hardware. Maintaining a single language eliminates friction. Here, Express operates as a rigid, stateless traffic controller, immediately sorting incoming requests into dedicated lanes for authentication, topics, and concepts. Watch this plain text password enter the auth pipeline. A bcrypt algorithm intercepts the text and transforms it into a one-way, randomized hash string. The original text is destroyed, ensuring a compromised database yields no usable passwords. Once a login attempt clears the hash check, the server issues a JSON web token. This cryptographically signed string returns to the browser as a stateless session manager. The server ignores the user's identity until the browser attaches this token to a future request. On the topics route, that signature is tested, and authentication middleware halts every incoming request, verifying the token's validity before executing a database query. The concepts route manages the dense operational logic. It provides specific endpoints for the complete lifecycle of a node, creating new entries, reading existing text, updating depth-level metadata, and deleting stale records. To guarantee uptime, a background process manager known as PM2 watches this entire API layer on port 3001. If a logic error crashes the node server, PM2 catches the failure and forcefully restarts the application in milliseconds. The middle-tier API holds no memory and saves no files. It operates strictly as a heavily guarded, stateless switchboard, verifying identity and routing traffic. At the foundational layer, this graphic maps the PostgreSQL relational data store. The database expands into 3 flat, strictly formatted tables. Because this database operates locally on the exact same physical server as the API, latency is practically 0. Queries execute at memory speed, completely avoiding the sluggish network hop required when querying a managed external cloud database. The schema begins with the users table. It securely houses the bcrypt hashed passwords and assigns every registered account a permanent unique integer ID. The topics table stores categorical data, like subject names and interface colors. Crucially, it contains a specific user_ID column to track ownership. The database enforces a foreign key relationship here. It permanently links a topic row to a specific user ID, making it structurally impossible to accidentally serve one person's research to another. Finally, the concepts table handles high-density storage. It records specific node names, depth levels, raw text notes, and related IDs necessary to render map edges. By demanding rigid data types and enforcing explicit relationships between tables, a relational schema acts as the ultimate architectural safeguard. It guarantees logical integrity at the base of the machine, long before a single byte travels back up the stack. Zooming out to the full macro architecture, this diagram connects a new external node labeled OpenAI directly to the front end. The application uses a bring-your-own-key model. Users paste their personal OpenAI API keys into local browser storage. By originating requests from the client machine rather than the central API server, the compute costs are successfully shifted off the application owner. During a deep dive, the browser packages a specific concept and the user's current knowledge depth, sending them to the GPT-4o model. The response returns in real time, streaming token by token directly onto the screen. To find new relationships, the system passes raw arrays of concept names to the model, instructing it to return a formatted JSON array of related concepts. These results are saved directly to the database to generate new physical edges in the graph. The application can also pass the entire graph topology to the AI. With visibility into every node and depth level, the model calculates optimal learning pathways and suggests the exact adjacent concepts the user should study next. To understand how public traffic interacts with this entire ecosystem, look at the server's outer boundary. This Nginx gatekeeper block monitors port 80. Nginx executes precise routing logic. If a user asks for the base web address, Nginx funnels them directly to compiled static files. If the URL contains the /API tag, Nginx proxies the request straight down to the node.js switchboard on port 3001. Code reaches this server via a manual deployment pipeline. A local machine compiles the build, then uses the secure copy protocol, authenticated entirely by cryptographic SSH keys, to transfer the updated files onto the server hardware. Whether generating dynamic learning pathways or routing live global web traffic, the operations are mechanically simple. Advanced features execute through optimized context passing, and production deployment is achieved through secure file transfers. Watch this data pulse trace the lifecycle of an AI request. It hits the Nginx date, clears express authentication, retrieves context from Postgres, queries the external language model, and paints the result onto the front end. There are no managed database services auto-scaling in the background. There are no serverless functions spinning up on demand. The entire sequence happens inside a single, explicitly defined environment. The client is just static files. The routing is plain JavaScript logic. The database is standard SQL architecture. Everything on a bare Linux machine. Relinquishing cloud abstractions forces a developer to confront the mechanics of the request lifecycle. Mastering these fundamental bare metal layers is the only way to achieve total ownership over an application's security, operational logic, and ultimate scale.